All right, we are going to do a wicked hard math problem. It's going to involve getting an exact, as in involving no decimals, answer to a very, very thorny integration problem. Now, we are going to be checking answers with decimals just to see. We're going to be finding this area, which is the area between these two graphs. You'll have to pardon me, I have a cold. Okay, I want to do this in a way that doesn't depend on technology or decimals or anything like that, but I will be using technology, decimals, and all that stuff to check things as I go along. First of all, I have to figure out where are these intersections. Anytime that you have to find the area between two graphs, unless you're given the limits of integration, you need to know where to integrate from and where to integrate to. Sometimes this is easy, sometimes it's not. Guess which one this is. We're going to find the intersection like this. Of course, it will be 2 sine x equals cosine of 2x. Now, this happens over and over, but we're interested in the first 2 times that it happens, like the problem says. I cannot solve a problem that involves sine of x and cosine of 2x. There are 2 problems there. First of all, sine and cosine are like kind of incompatible, but the x and the 2x, that's a real deal breaker. I need to change the 2x into x. I'll do it using this. You may remember these from pre-calc. If you don't, you can go back and review. Cosine of 2x is cosine squared of x minus sine squared of x. Now, this also can be put into a couple of different forms. It can be put into the form 1 minus sine squared of x, like that's cosine squared of x, isn't it? Take a second to check. Yes, because sine squared of x plus cosine squared of x is 1. That means 1 minus sine squared x is cosine x, or cosine squared of x. And 1 minus cosine squared of x is sine squared of x. Okay, so we're actually going to do both of these substitutions one after the other to come up with 2 alternate versions of this. This is 1 minus sine squared minus another sine squared, where this is this one and this is this one. Now, obviously, those last 2 are like terms. So we get this alternate form of cosine of 2x. I'll say, or I could say it's equal to, and now going back to this original version, instead of turning cosine squared into 1 minus sine squared, I'm going to turn sine squared into 1 minus cosine squared. So I'll do cosine squared of x minus 1 minus cosine squared of x. This is not grade school. We are not going to say these cancel. We're not, that naive anymore. The minus sign distributes, and then they become like terms. This is cosine squared plus cosine squared, making it 2 cosine squared of x minus 1. These are the 3 versions of the identity for cosine of 2x. Now, I want to choose the version of this to substitute into this equation that will cause the equation to become solvable. If you're looking at the 3 of these, you probably gravitate toward this one right here, 1 minus 2 sine squared of x. And if you do, you're smart, because that matches with 2 sine of x. So the first thing to do to this is to turn it into 2 sine x equals 1 minus 2 sine squared of x. This is good news, because now everything is sines and there's no more 2x. What I'm going to do is get everything on one side so that I can do a factorization or whatever. So this becomes 2 sine squared of x plus 2 sine of x minus 1 equals 0. Now, if you're like me, you see this and you think, I'm going to factor. Well, good luck. One way you can check to see if something is factorable is, now you may have had this experience. when you decide something isn't factorable and you go and solve it with the quadratic formula, but then the thing under the square root ends up being a perfect square, and so you don't end up needing to write square roots in your answer, you've probably done that before and you've been like, oh crap, I could have factored it the whole time. We're going to do that sort of check. We're going to check if the thing under the square root is a perfect square. The thing under the square root, you'll remember, is b squared minus 4ac. So b squared minus 4ac is 2 squared minus 4 times 2 times negative 1. Okay, 2 squared minus 4 times 2 times negative 1. 2 squared is 4, of course. And then this is minus 4 times 2, which is 8, and then times negative 1, which turns into plus. 4 plus 8, which is 12. Now, everybody and his brother knows that 12 is not a perfect square. That means that if I try to factor this equation, I'm out of luck. So the only thing I can do is use the quadratic formula. Sine of x, not x itself, but sine of x equals, and now I'm going to do negative b plus or minus square root of b squared minus 4ac all over 2a. So negative b is negative 2 plus or minus square root of b squared minus 4ac. Now, if you're dumb like me, maybe you'll do the whole thing again. But if you're smart, you'll realize it's already been done. And do it. Now, in case you think that I'm smart because I saw it, that was actually because somebody pointed it out to me. So I'm dumb and they're smart. So negative 2 plus or minus square root of 12 divided by 2 times a is 4. This is negative 2 plus or minus. And at this point, if you're taking Calc BC, I'm guessing you know how to simplify square roots. A 4 pulls out and becomes a 2. 2 root 3 over 4. And now negative 2 and positive 2 can both reduce. This becomes negative 1 plus or minus 1 root 3 over 2. Okay, like a lot of quadratics, this has 2 solutions. But like sometimes happens in these problems, you get one solution that's actual garbage. So I want to write them with some care. So sine of x equals negative 1 plus root 3 over 2, or this is supposedly the other one. And I'm like, hey, we're looking for the first 2 intersections. This is good, right? Because we've got 2. No, that's wrong. Here's why. Sine of x cannot possibly be equal to this. Here's why. Root 3 is about 1.7-ish. That means that this is about negative 1 minus 1.7 over 2, or negative 2.7 over 2, or about negative 1.35. Now think about it. Sine and cosine are those functions that live on the unit circle and cannot exit the unit circle. That means it can't possibly get all the way down to negative 1.35. Sine of x can only be as low as negative 1. So that's why this is an invalid answer. Whereas this one right here, because you do plus root 3, this is like negative 1 plus 1.7-ish, and then over 2. Well, negative 1 plus 1.7-ish is going to be about 0.7, and then divided by 2 is about 0.35. That's good. That's within the boundaries of what sine can be. Okay, but it is sine of x equals this, not x equals this. So x is equal to the inverse sine of negative 1 plus root 3 over 2. And because I'm kind of a stickler for details, I'm going to say this, I don't really like writing minus signs when I could write subtraction signs. So root 3 minus 1 over 2. Okay, so if you take out your handy dandy calculator, you can come up with an estimation for this. This is, let's see, root 3 minus 1 over 2. That's like 0.366 or so. Oh, wait, hang on. I wanted to go up here and compare it to that, but no, we need to do something to it first. Yes. Yeah. So this is one time where they intersect. Then we're gonna get another time when they intersect. Hang on, let me think. Are we doing this right? -1 plus √3 over 2 √3 minus 1 over 2. Oh, you know why? I got a wonky answer because I wasn't taking the inverse sine of that because I'm a great big doofus. Okay. So this is 0.374. And lo and behold, that is the lower limit of integration. Now, how do you find the upper limit of integration? Obviously, we know that it's about 2.767, but I want to be able to get it exactly. Now, what we want is the next time that this is true. To get the next time it's true, you have to know your unit circle. Here's a circle. And sine takes on values twice, right? Now, this is some small positive number. So I know that right here, sine is √3 minus 1 over 2. I don't know what this angle is, and I don't care. I just know that sine is equal to √3 minus 1 over 2 somewhere in the first quadrant. There's another time it's equal to that, and that's in the second quadrant. And it's also equal to it here. But think about it. What angle is associated with each one of these? Here, in the first one, this is an angle of inverse sine of √3 minus 1 over 2. Okay, cool. Here, this is really tricky. It's pi minus √3 minus 1 over 2, or pi minus inverse sine of that. So this is pi as in wrap around to pi and then subtract the same amount that was counted up right here. It's very tricky. So pi minus inverse sine of √3 minus 1 over 2. So the lower bound of integration is going to be inverse sine of √3 minus 1 over 2. And the upper will be pi minus inverse sine of √3 minus 1 over 2. This is a serious buzzkill, though, because I don't want to have to keep on writing so many symbols. So I'm going to do something where I let n be equal to inverse sine of √3 minus 1 over 2. I'm just going to put in a symbol for it so that I can like write something convenient. And then the lower will be n itself. And the upper is pi minus n. Okay, it's just to make it a little easier. We will need to actually use what n is, but this is just to make writing it over and over easier. We should verify that pi minus n is this. Well, think about it. We know that 0.375 is about what the n is. So now let's do pi minus 0.375. I get 2.767 on my calculator. So we know that we have like bounds of integration that are verified by the Desmos graph. Okay, now which graph is on the top? We haven't even answered this question yet. Which one is above and which one's below? You have to pay attention to this because you don't want to, by mistake, end up doing integral of bottom minus top. And that's not so good. So here's how you can do it. First of all, we know what's coming because here, this is obviously 2 sine of x. And this is obviously the cosine graph. So we kind of like know by cheating, which is good. We know by cheating that sine is on the top. But let's watch it happen. We can actually go and figure this out. What is between the 2 times when these are equal? Keep in mind that they're equal here and here. Ah, okay. So right here at pi over 2. Pi over 2 is between the intersections. So now we're trying to address the question of, is 2 sine of x or cosine of 2x on top between n and pi minus n? When we know that pi over 2 is between them, and so I'm going to use that as a test point. So at x equals pi over 2, 2 sine of x equals 2 times sine of pi over 2. Sine of pi over 2 is where y is 1, so this becomes 2 times 1, or just 2. So bam, that's what 2 sine of x is equal to. And cosine of 2x is cosine of 2 times pi over 2. That's cosine of pi. And cosine of pi is the x-coordinate of the leftmost point on the unit circle. So that's -1. All right. This tells us that 2 sine x wins. It's on top. So we finally have an actual integral to write. The integral will be this. Integral from n to pi minus n. Don't worry, again, we're going to be putting in n as it actually is, of 2 sine x minus cosine of 2x. Now, I'm going to go through this kind of fast because I'm assuming you know how this works. Integral of sine is negative cosine, so this will be -2 cosine x. And then for the second part, yes, use substitution, but you kind of know what's going to happen from now, like, because you've been doing it for a while. So minus sine of 2x. I know the derivative of sine of 2x is cosine of 2x, except that I also multiply by 2. So to take care of that, I divide this by 2. And now I know that if I take the derivative of this, it's going to be 2 from the chain rule times cosine 2x, and that 2 and this 2 cancel to give me back this. Okay, so this is my antiderivative. I'm now going to be evaluating it at n, that's the whole inverse sine thingy, and pi minus n. I want to rewrite this one more way, because this is going to be -2. Well, hang on, I'll tell you how we're going to do it. We're going to use the fact that sine of 2x, that's right here, is equal to 2 sine x cosine x. This is another one of those trig identities from pre-calc. So this is going to be equal to -2 cosine x minus 2 sine x cosine x over 2. Well, the 2's cancel, right? And so really this is just minus sine x cosine x. Now I'm going to write the actual n thing. This is from inverse sine of √3 minus 1 over 2 up to pi minus inverse sine of √3 minus 1 over 2. In case you think we're close to being done, we're not, because look at what we're going to actually have to do here. We're going to need to take the cosine of this and the sine of this. And then we're also going to have to deal with the fact that we've got pi minus it, and we'll have to deal with what that implies. So I know the answer is going to involve this cosine of inverse sine of root 3 minus 1 over 2. If you if you remember this from your pre-calc days, then you'll know that this interior function here entitles you to write a triangle. So this right here, this implies a triangle. This is a triangle with an angle whose sine is root 3 minus 1 over 2. So I'm going to draw such a triangle, right triangle, obviously, and I'm going to position an angle right here, and I'll call this side root 3 minus 1, and this side 2. With the angle written like this, the sine of that angle is, think opposite over hypotenuse. It's root 3 minus 1 over 2. But what I really want is the cosine of that angle. Now, in order to get the cosine, I need to know the length of this side. Because I know two sides of the right triangle, I can figure out the third side using Pythagorean Theorem. It's not going to be nice, but I can do it. I'll call this b in the spirit of Pythagoras. So I know that b squared plus root 3 minus 1 squared has to be equal to 2 squared. Okay. Well, I ate my foiling Wheaties today, so I know that this is root 3 squared, which is 3, minus 2 times 1 times root 3. So that's minus 2 root 3. And then minus 1 times minus 1, that's actually plus 1 squared, or plus just 1. And that equals 4. All right. B squared plus 3 plus 1. Oh, yeah, that's 4. B squared plus 4 minus 2 root 3 equals 4. The 4s can be taken away. So I'm left with b squared equals 2 root 3. And this is really messy. I don't like writing multiple roots like this, but b is going to be equal to the square root of 2 root 3. Now that's like blah. I don't want that. So what I'm going to do is actually back up to this point, and I'm going to get this into a single root. Now, usually you talk about pulling things out of roots. What about putting them back in? The 2 can be thought of as a 4 that has come out. So 2 root 3 is square root of 12. Now comes the magic. B is going to be the square root of the square root of 12. Think of exponents. Square root is to the 1/2 power, right? Half power to the half power, that's 1/4 power. So this is really the 4th root of 12. That means B is 4th root of 12. And so cosine of that n thing is 4th root of 12 over 2. Now, sine of it, sine of inverse sine of anything, simply strips away the sine and the inverse sine because they cancel out. It doesn't always happen in the reverse order, but as long as the thing inside, the root 3 minus 1 over 2, can be put into inverse sine, as if it's the inverse on the inside and the forward function on the outside, they always just annihilate each other. So this is simply root 3 minus 1 over 2. Okay, so I've got these that I'm starting to piece together. These are going to be like the ingredients for evaluating the integral. Now, what about this thing up here, this pi minus whatever? All right, I'm going to show something in general. I'm going to show what sine of pi minus something is and what cosine of pi minus something is. Those are actually like really simple to express. So I'll put that up here. This will be in general. Sine of pi minus anything. Think about unit circle. You can prove it with a sum formula as well, but think about it. This is the normal thing. This is n, and then this is pi minus n. They are at the same level, vertically speaking. So sine of pi minus n is going to be the same as sine of n. It makes no difference. Cosine of pi minus n, now we're talking about the horizontal. Horizontal is flipped. So this is negative cosine of n. We're talking about this horizontal position versus this one. Oh, okay. So this is the negative, right? You got to watch out for that. So here's what we're dealing with. I'm going to summarize here. So cosine of the n we were talking about. This is a summary. Cosine of, this is a little close. Cosine of n is fourth root of 12 over 2. Sine of our n is root 3 minus 1 over 2. Cosine of pi minus n is negative cosine of n, which is negative fourth root of 12 over 2. Whereas sine of pi minus n is equal to sine of n, which is root 3 minus 1 over 2. Okay, so these are the values we're going to actually need. Now I'll go and grab this. I promise we're getting close. We actually really are. I'm not lying, even though I would. So, okay, this is what we want to evaluate. Now I can go back to calling this n, because I just want to. I hate writing big, complicated things. And anyway, I've got the things to plug in here. There's no need to keep on writing the ugly thing for n. All right, very close now. This is negative 2 cosine of n minus sine of n times cosine of n. Oh, crap. No, wait, hang on. If you said he's doing it wrong, you were right. You got to put in the top one first. Sorry, this has been like half an hour so far. So this is negative 2 cosine of pi minus n minus sine of pi minus n times cosine of pi minus n. And that's the pi minus n version. Now it's subtracted by negative 2 cosine of n minus sine of n times cosine of n. It's about to get simpler, because remember that this cosine of pi minus n, this is, let's see, this is, bingo, right up here. It's negative fourth root of 12 over 2. This is sine of n, which is root 3 minus 1 over 2. This cosine of pi minus n, we already did that, right? That was right here. So we can just copy that. That's negative fourth root of 12 over 2. Cosine of n is fourth root of 12 over 2. And sine of n times cosine of n, this is going to be root 3 minus 1 over 2 times, in quantity, fourth root of 12 over 2. Now we just need to be careful with minus signs and distributing and all that jazz. So we've got the -2, don't forget that matters. -2 times negative fourth root of 12 over 2 minus root 3 minus 1 over 2 times negative fourth root of 12 over 2. So far we've done this, this, and this. And now it'll be minus, okay, the minus signs can make your head spin here, but it's minus -2 times this. So -2 fourth root of 12 over 2. Don't worry, we're going to be simplifying a lot in here. And then minus root 3 minus 1 over 2 times fourth root of 12 over 2. All right. So some simplifying can be done here. These minuses become a plus. The 2's go away. These minuses also become a plus. And this minus sign hits here and here, turning everything into plus signs. So we don't have to worry about subtracting anymore. Everything has become plus, right? Oh, there's one I didn't hit, but yeah, that's a plus sign as well. So now I can write this as fourth root of 12. That's that part, plus, let's see, root 3 minus 1 times fourth root of 12 all over 4, because that's 2 times 2. And then plus, well, all of these are, well, this is over 2. So this is, oops, no, wait, that's a reduction that could happen as well. So 2 and 2 can reduce. It's easy to lose track of this. Then plus, on the inside there was fourth root of 12, right? So as of now, we've gone up through here. And then plus another root 3 minus 1. Yep. Root 3 minus 1 times fourth root of 12 all over 4. Okay. So one thing I notice here is that there's a fourth root of 12 absolutely everywhere, right? So I can take that out. I can say fourth root of 12 is a factor absolutely everywhere. And so I end up with 1, that's from here, plus root 3 minus 1 over 4. And so far I've covered up to here, plus another 1, that's here. And then plus another root 3 minus 1 over 4. So this becomes, if I combine like terms, these are like a fourth plus a fourth. That means that it's going to end up being root 3 minus 1 over 2, or fourth root of 12 times 1 plus 1, that's 2. Yes, 2 plus root 3 minus 1 over 2. And now these really are, actually like terms. Yeah. So I can write this as fourth root of 12 times 2 plus root 3 over 2 minus a half. Minus a half, if I do 2 minus a half, that's 4 halves minus 1 half, that's 3 halves. And I get 4th root of 12 times 3 halves plus root 3 over 2. And if you really want to do as much factoring as possible, you can get this out to 4th root of 12 over 2. That's taking these out, times 3 plus square root of 3. Now you can use a calculator to verify that this is actually the same as the value of the integral. I encourage you to visit the website wolframalpha.com. It can do integrals for you to a shocking degree of precision. And what you end up with when you do this is this exact value, the 4th root of 12 over 2 multiplied by 3 plus root 3 is about 4.40. And integral, when you do the integral with a computer, that gets the same value. So this is a real marathon problem. There's just so many things that you have to unexpectedly pull off the shelf. You have to know trig identities. You have to know how to transform things with triangles. You have to know pi minus n and how that affects sine and cosine. You got to know like sine of 2x, cosine of 2x. There's really a lot that gets pulled off the shelf. And that is why I wanted to do this video, because it involves so many things that you have to know how to go and grab, which I think, frankly, is really cool.